Let's take a look at a few free body diagram practice problems. So the first practice problem we have is drawing a free body diagram for a book that is sitting on a table. Well, the first thing we need to do is identify what forces are acting on that book as it sits on the table. We'll quickly note that force gravity is pulling this book down. We know that gravity is always present in every scenario, so we have gravity pointed down. Another thing to note is that we have a table that the book is laying on. The table is a flat surface, so because it's a surface, it's going to exert a force upward. In this case, that's a normal force pointed up. We notice that this book is at rest, and because it's at rest, it means that these forces are balanced. We also can see from our photo here that these forces are balanced because the upward normal force is the same size as the downward force of gravity. So those two forces will end up canceling each other out. Let's look at our second problem. This one says draw a free body diagram for a girl that is rollerblading as she moves towards the right at a constant velocity. Key word here is constant velocity. Because it's a constant velocity, we already know that forces are balanced, because a constant velocity means that we are not accelerating. The first force we're going to identify is always the same force, and that's force gravity. And we know force gravity points down. Looking at the problem, we can see that they are rollerblading on a surface. So because a surface is involved, we're going to have a normal force pointed perpendicular from that surface. Next, we know that the girl is rollerblading to the right, so we can clearly see that she is pushing her rollerblades on the ground to the right at the moment. So we have an applied force pointed to the right. Lastly, because she's moving to the right, we're going to have a force pointed in the opposite direction of motion, and that's going to be friction. So we need to remember that this girl is moving at a constant velocity. Because it's a constant velocity, it means that our forces are balanced. So that means that our applied force is going to be balanced with our frictional force. And that also means that our normal force is going to be balanced with our force of gravity. That just means that the magnitude of these forces are going to equal each other. Let's take a look at another example here. It says draw a free body diagram for your crate that is being pulled by a rope. That's important that it's a rope towards the right, and it is not accelerating. Okay, so not accelerating tells us again that this is balanced. So here's our crate. All right, here's our rope. So if we go ahead and draw our free body diagram here, we're going to start with the first one that we always know is present, and that is force gravity. Got force gravity pointed down. Next, our crate is on a flat surface, so we're going to have a normal force pointed up. And then we also have this person pulling, but they're pulling with a rope, so we should have force tension pointed to the right. And then lastly, it's not moving, so we need something to balance out force tension. We need a force in the opposite direction. Well, the opposite direction of motion, if it was moving, would be friction. Therefore, we're going to have force friction pointed to the left. Again, force normal is equal to force gravity, and we know that force tension is equal to force friction. So here's our next problem where we have a cow and a lawn mower. Get it? Lawn mower. So it wants us to draw a free body diagram for a lawn mower. It gets funnier every time I say it. That is being used by a cow and is being pushed to the left. Well, let's start with the force that we always know is present. Gravity. Force gravity points down. From there, this lawnmower is being pushed on the ground, so we should have a force normal pointed up from the ground. We know that the cow is pushing to the left, so therefore, if it's moving to the left, we should have friction to the right. And then also we know that this cow is pushing downward on this lawnmower. So because it's pushing down at an angle, we're actually going to end up with an applied force pointed down at that angle. It doesn't tell us if we're moving at a constant velocity or if this lawnmower is speeding up or slowing down, so we don't know if we're balanced or unbalanced at the moment. We will know that the forces in the y direction, so the net forces in this y direction that either point up or down, are balanced. And the reason why we know this one is because this lawnmower isn't moving off the ground. It's not speeding up towards the moon, and it's not speeding up towards the middle of the earth. It's just moving flat on the surface because we've all mowed a lawn before, right? We have to do it for our chores or whatever, but we've all done it, and we know that lawnmowers don't magically start floating up into the sky or falling down into the earth. Again, we don't know, though, if the net force in the x direction, and that x direction means this direction here, is balanced or unbalanced. Something else that's important to note here is that this applied force is at an angle. And because this applied force is at an angle, part of it is in this x direction here, and another part of it is in the y direction. This is important, but it's also something that we're going to talk a lot more about later on. All right, here's a bonus practice problem. Draw a free body diagram for the skateboarder that is rolling down the ramp at a constant velocity. So again, constant velocity is telling us that we are balanced. So we know that all of our forces on this object are balanced. We can see that this ramp is like on an angle here, but even though it's on an angle, we still will have gravity pointed straight down. Gravity will never point at an angle. Because our skateboarder is moving down this ramp, we're going to have friction pointed in the opposite direction. Our skateboarder is moving in this direction. So therefore, we should have friction pointed in the opposite direction. And we notice that friction now is pointed at an angle. The reason being, this person's motion is at an angle. Lastly, we have force normal. And we said before that force normal points perpendicular from a surface. So because this surface is at an angle, force normal will no longer just point straight up. It will point at an angle from this surface. So here is our surface. Here is perpendicular from that surface. So we should have force normal pointed something like this. Perfect. So because we know they're moving at a constant velocity, that's telling us that net force in the x direction and net force in the y direction, even though we're at an angle, are all balanced. So just a little sneak peek of what this would look like if I were to write my equation for my net force in the x and my net force in the y. I would have to divide these forces up into their x and y components. So the normal force, I would have an x direction that points like this, and friction force, I would have an x direction that points this way. I would also have a normal force y direction that points up, and a friction force y direction that also points up. Because my skateboarder is moving at a constant velocity, that means that my normal force in the x direction is going to be equal to my friction force in that x direction. Again, because it's a constant velocity, that also means that my force gravity in the y direction is going to be equal to my force friction in the y direction plus my force normal in the y direction. And how do I know that I'm supposed to add these together? Well, like I said, we'll touch on this in the future, but the way I know is that the normal force is pointed up here and the friction force is pointed up here. Because they're in the same direction, I just add them together. So let's take a look at our last problem. And we're being asked to draw a free body diagram for Dr. Freitas as he skydives with no air resistance. What a daredevil. So again, we need to remember what force is always present in every situation. Well, that's force gravity. Now we need to think what other forces could be present on Dr. Freitas while he's in the air. Because there's no air resistance, there's actually no other forces acting on Dr. Freitas. So it's only force gravity acting on him. And because it's only force gravity acting on him, we would see that these forces are unbalanced. And again, unbalanced forces means that he is accelerating. In this case, he would be speeding up, which makes sense because if you jump out of a plane and you go skydiving, you speed up once you jump out of that plane. Eventually, though, your acceleration will taper off and you'll reach what we call a terminal velocity, but that's a conversation for another day.